Now you have seen a lot of instances, examples on how to use your Henderson-Hasselbalch equation. So you are now ready to learn how to prepare buffers using this equation. This is actually the main objective of this module, for you to learn how to prepare buffers. All students who are in an introductory course to biochemistry, this is the first thing that they learn or should learn. Let's proceed to the problem. A student wants to prepare a 500 ml, zero point 0.5 molar ammonia ammonium buffer with pH 9. There is concentrated ammonia and solid ammonium chloride available in the stockroom. How will the student prepare this buffer? So again, write down your Henderson-Hasselbalch equation. So let's write it first and see if we have any given values needed in this equation. Actually, before that, we need to identify the components of our buffer. So we have the two ingredients. So we have ammonia and ammonium. So between these two, ammonia should be our base. So we will put the concentration of ammonia in the numerator, and ammonium is our weak acid. So we will put ammonium in the denominator. Now notice we are given Kb. The given is Kb of ammonia. That's 1.8 times 10 raised to negative 5. But we need the Ka. Recall, okay, Kb for a weak base, so this is the Kb for ammonia. You can actually determine the Ka for the conjugate acid. So you can determine the Ka for ammonium. And how do you do that? So recall the relationship of Ka and Kb for conjugate acid base pairs. So their product is equal to the ion product constant of water, Kw, which is equal to 1 times 10 raised to negative 14. This is a constant. So to get Ka, we just need to divide 1 times 10 raised to negative 14 divided by 1.8 times 10 raised to negative 5, and this will give us 5.56 times 10 raised to negative 10. So we can now get pKa. pKa is equal to 9.25. So now we have the value of pKa in our Henderson-Hasselbalch equation. So what else? What other given information do we have? We have the target pH, pH 9. So that will be the value that you will substitute for pH in this equation. Now, we don't know the concentration of our components. Always remember that when you are given the concentration of a certain buffer system, if you are not given the individual concentrations of your components, if you have something like this, a 0.5 molar buffer, it doesn't mean that you have zero point 0.5 molar ammonia and zero point 0.5 molar ammonium. No, this zero point 0.5 molar is the total concentration of the two components. So we actually have another information from this part of our problem. It means that zero point 0.5 molar, this is the sum of the concentrations of ammonia and ammonium. So the concentrations of these two is equal to zero point 0.5 molar. So now, if we isolate concentration of ammonia on one side of this equation, we can substitute the concentration of ammonia in our Henderson-Hasselbalch equation with this expression. So let's write our equation with the plugged in values. So we have 9, our target pH, equal to 9.25 plus logarithm of 0.5 minus the concentration of ammonium divided by the concentration of ammonium. And now we are left with one variable. So you can solve for the concentration of ammonium from this equation. So I'm leaving the solution to you. Try it on your own. So you should get a value of 0.32 molar. And it follows that the concentration of ammonia is 0.18 molar. So these are the information we get from our Henderson-Hasselbalch equation. But we are not yet finished with this because we are asked to describe how the buffer is prepared. So how do we do this? We need to determine how much of the reagents we need to mix to get the buffer that the student wants. So let's start with ammonia. So in the buffer, we need 0.18 molar. And our available reagent is the concentrated ammonia, which is 18 molar. So we need 500 ml of the buffer. In this 500 ml of buffer, the concentration of ammonia must be 0.18 molar. So for that, we will use the dilution formula. So if you recall, the dilution formula is M1V1 equals M2V2. So initial concentration times initial volume is equal to the final concentration times the final volume. So we have the initial volume, which is the volume of the concentrated ammonia, 18 molar. We want to know how much of this 18 molar ammonia solution is needed in the 500 ml buffer to give us a concentration of 0.18 molar. So this will give us a value of 5 ml. Next, for the solid ammonium chloride. So what should be the mass of the solid ammonium chloride that will give us a concentration of 0.32 molar? So this is the concentration of ammonium in the 500 ml buffer. So how do we do that? So again, we need the mass of ammonium chloride. So our basis is this. We start working on the 0.32 molar or 0.32 mole per liter times we want a solution that has a volume of 0.500 liter or 500 ml times. This one is the molarity of ammonium. So we need to relate how many moles of ammonium ion do we have in 1 mole of ammonium chloride. And it's 1:1, right? So 1 mole of ammonium in 1 mole of ammonium chloride. And finally, we convert this using the given molar mass of ammonium chloride. That's 53.91 grams per mole. So the mass of ammonium chloride required for this buffer is 8.6256 grams. So now you have performed the calculations. So how should you prepare this buffer? So you get first, or you measure first, your solid ammonium chloride. So after measuring your solid ammonium chloride, you have a beaker. Let's say you have 400 ml of distilled water in your beaker. And then you dissolve your solid ammonium chloride. So after it completely dissolves, you add 5 ml of the concentrated ammonia. Then check the pH. So use a pH meter to check. If it's not equal to 9, you use either a strong acid like hydrochloric acid or a strong base like sodium hydroxide to adjust the pH. After adjusting the pH, you add the necessary amount of water so that the final volume will be 500 ml. So this is how you use your Henderson-Hasselbalch equation in buffer preparation.